The IEEE Photonics Journal Club is a regular gathering of scientists that will review scientific papers found within our research journals. It was created to help connect students and early career professionals with researchers and authors of prominently published papers. So it's become a really great mentorship tool within our society. Participants read chosen scientific papers picked by an editor-in-chief of a said journal, and then attend a session with published authors. The authors present their published research, where participants can ask direct questions about the work. So in Ask All today, if you have any questions about the research, the peer review process, how to get more involved as a volunteer of our journals, there's staff that will be monitoring the chat to share that information, but there also will be an open Q&A at the end of today's session where you can ask questions directly to the authors. So for today's session, we have two authors and speakers today from popular papers within JSTQE. However, we have a great moderator today, Ivana Gasula from ITMQV in Spain. Her research focuses mainly on the application of multi-mode and multi-core fibers to distributed signal processing, particularly in the area of microwave photonics. She has received the prestigious Consolidator grant from the European Research Council and is also a co-founder of the spin-off company iPronics Programmable Photonics. The results of her work have led to more than 150 international publications. She has served on the TPC of a variety of conferences, including OFC and ECOC. Additionally, she is the senior editor of the IEEE JSTQE and an associate editor of the IEEE Optica Journal of Lightwave Technology, among other journals as well. So I will kick it off to Ivana now. She will share more information on our presenters and authors today.
Thank you very much, Lauren. It's a pleasure to be able to participate in this Journals Club session. The first author is Istvan Gion. So Istvan affiliation at background is with the School of Engineering, Institute for Integrated Micro and Nano Systems at the University of Edinburgh in UK. Istvan Gion received a Master's in Engineering and the PhD degrees from Oxford University in UK in 2003 and 2008, respectively, following a period in industry where he worked on processors for smartphones and a cloud-connected activity tracking system for dairy farms. He joined the University of Edinburgh. He is currently a lecturer and is developing single-photon avalanche diode cameras and exploring applications in 3D capture and the life sciences. So please, Istvan, you can start whenever you want.
Thanks so much for the introduction, Ivana. And let me just say I'm very grateful for the opportunity to speak here. So I'm just going to share my slide. Okay, right.
Looks great.
Thank you. So I do have a lot of slides. I hopefully I can get through most of them. Right. Okay. Yeah. So this paper is about the design of a time-of-flight or LiDAR sensor. Now, these sensors are used for depth or 3D imaging in a wide range of applications. So, for instance, smartphones for autofocus assist, robotic vacuum cleaners for obstacle detection, in drones for landing assistance. They're also used in last mile delivery robots, self-driving cars, and airborne and spaceborne mapping. I'm sure there are some additional applications as well, which I will mention here. Now, here, in terms of this paper, the target was to develop a flash LiDAR sensor, so a LiDAR sensor without moving parts for outdoor operation to basically provide high-speed 3D vision for robots over tens of meters. That was the target here. Now, to track back a little bit, how does LiDAR actually work? So in LiDAR, we illuminate the scene of interest with a modulated light source, such as a pulsed laser source. And then there's a receiver which detects the backscattered light returning from objects in the scene. And then by timing the arrival of this echo, we can measure distance and therefore build up a 3D image or depth map of the scene. Now we can distinguish between a solid state and mechanical scanning LiDAR. Now in the solid state case, we use diffuse or flood illumination to illuminate the whole scene of interest, and the receiver is typically an image sensor or a 2D area of detectors. On the other hand, in a scanning system, there may be a single detector paired with a single laser source that raster scans the scene as shown here using a mirror. However, it is more common these days to use pairs of lasers detectors to capture parallel lines simultaneously. Now, comparing the two methods, solid state is more robust to shocks and vibrations and different weather conditions. In addition, it can be made into a cheap and compact module due to lack of mechanical parts. And because it's capturing the whole scene of interest at the same time, there tends to be less motion artifacts. However, there are also some significant challenges compared to mechanical scanning. And one of the challenges being that solid state will typically generate much higher data rates due to the larger detector array. And it also requires a large number of timing units for this highly parallelized acquisition. Now, in the case that the receiver is a SPAD or a single photon avalanche diode array, it usually operates in a so-called time-correlated single photon counting modality. And what that means is that the photons detected by each pixel are timed with respect to the laser source, and then a timing histogram is composed for each pixel as shown here. And then by extracting the time of flight corresponding to the peak in histogram, the depth of the surface observed by a given pixel can be determined. So in this case, depth of the type of the car. Now, what are the advantages of SPADs in LiDAR? So what happens is that for each detected photon, the SPAD will output a discrete voltage pulse as shown here, with the leading edge of this pulse encoding the time of arrival of the photon with essential picosecond precision. So therefore, there's potential of extracting precise depth estimates from just a handful of these photons. Another significant advantage is that because SPADs can be implemented in CMOS processes, we can build arrays of them, large arrays of them with integrated processing for basically an all-digital single-chip receiver. Now, there are some considerable challenges as well in addition to these advantages. So the sensor must be able to extract depth information at sufficiently high rates, and even under very high ambient levels, up to 100 kilolux in, for instance, automated LiDAR, and without getting overwhelmed by the high rate of background photons. And what this requires is an architecture with suitably high photon throughput, and bearing in mind that each individual SPAD can fire at tens of megacounts per second. We do also need a scalable architecture, because ideally we want to achieve high resolutions, ideally, say, megapixel resolutions. Now, to cope with these demands, especially high photon throughput, there has been a trend not just to time photons on chip, but also to generate photon timing histograms, which then results in considerable data compression and hence alleviate some of the readout bottleneck issues. And what I'm showing here is some of the some recent sensors having such functionality. Now, the processing can be carried out in pixel, as shown here, or outside the array, potentially as clone parallel logic, or it can be a combination of the two. Now, the advantage of in-pixel processing is that it avoids any bottlenecks in transferring data, or so photon data out of the focal plane array. However, the disadvantage is that we then have limited space for histogram storage, because the limited circuit area available within the pixels, that then impacts the number of histogram bins we can have in our photon timing histogram. On the other hand, if we carry the processing outside the array, then the pixel array can be made dense and compact, as illustrated here. But there could be bottleneck issues under high ambient conditions, say when multiple paths in a column are sending events the same shared timing unit, or so-called time to digital converter. Also, in this second architecture, there will be a lot of memory will like to be needed outside the array, and then trying to shift data in and out of that memory can have frame rate and power consumption implications, as well as, and then in turn potentially limit scalability. Now, to avoid the large memory requirements associated with full-scale histograms, has become popular to apply multi-step, so-called multi-step partial histogramming approaches instead, which typically use just 16 or 32 histogram bins. And this slide basically shows two of the most common approaches. So we have the zooming approach, which starts with histogramming the whole time range at first, using a limited number of bins. And then in each step of the histogramming process, the peak bin is identified, and the histogramming logic zooms into the corresponding time range, eventually homing in on the signal peak. Now, in the second approach, I call a sliding approach, what we have is that the partial histogram is swept to the full time range, covering the entire time range over multiple steps. Now, one could argue that the zooming approach is more efficient in terms of the number of steps required for depth measurement, but it can get quite challenging under high ambient levels when there's a large build-up of background count for the initial steps where we have very wide bin width. Now, for our chip, we decided to adopt the time sweep approach, but rather than continually scanning the whole time range, we designed pixels which lock onto the peaks and track them. And this way, there's essentially an increase in the temporal aperture for signal photons. So more the signal photons are collected, they'll be more photon efficient from that perspective. And also, as we will see, the approach provides a mechanism for detecting motion in the observed scene. Here's the imager we developed. So it has 64 by 32 macropixels. And each macropixel has 4x4 studs plus a processing unit. Now, each macropixel generates an 8-bin histogram, which is then shifted in time automatically to locate and track peaks. And to enable this, each macropixel has an independent time gate, which is then controlled by the pixel itself. And we have up to 128 of these time gates available. And then readout is over 64 100 megahertz output lines. This slide shows the block diagram of macropixel. So histogram mode, what we have is the output of the 4x4 paths combined using an OR tree, and then sent to a multi-event time-to-digital converter, whose output goes to 8 12-bit counters, which represent the histogram bins. And then the contents of these counters are processed at the end of each exposure to estimate the background photon level, to detect peaks, and then to move the time gate position accordingly. Now, in addition to the histogram mode, there is also a photon counting mode or intensity imaging mode, which is indicated by this path. And in this modality, the paths are combined in pairs, and then each histogram bin is repurposed to serve as a photon counter for that pair of paths. And to illustrate the peak tracking functionality, what we have here is example histograms captured by macropixel over 4 consecutive exposures. So initially, what we see here is that the pixel is at time grid position 0, and then the estimates the ambient level at that position, and then based on this ambient level, peak threshold is computed according to Poisson statistics. Now, in the next exposure, the time gate is shifted to position 1. And now in position 1, the time gate is the last is found to exceed the threshold. But as this is an outlying bin, the time gate is then moved again in as far as exposure 3 is concerned to bring the peak into the middle, as we see here. And as the peak is now contained in the middle bin, the time gate position is then unchanged for exposure 4. It's not indicated in diagram, but what we have is the estimated background level being updated after every time gate shift. So I'm going to show some example data now. So this was obtained in the photon counting or intensity mode. Now the raw image which you see here on top is somewhat bulky, and that's due to the uneven spacing of the pixels horizontally, which results from the gaps created by a processing unit in each macro pixel. But by accounting for this uneven spacing and applying interpolation, we can get a somewhat better defined image as shown here. Now, here what we have see some results for short range imaging. So in this case, there's no need to use the tracking functionalities. The pixel time gates are just fixed at the first position. And what we have several panels here. So this panel A shows the RGB image of the scene, and then this panel B is the depth after a single 1 microsecond exposure. So this is obtained at the high speed of 1 kiloframes per second. And after by applying peak extraction to histogram frames, essentially. In terms of panel C, what we've done is that we're enabling one spot at a time within the macropixels, and then combining the resulting frames for a high resolution depth map. So we're recalling here that each pixel is actually composed of 4x4 spots. This is the sequential enabling of those 4x4 spots. And then finally here we've combined 20 higher of these high resolution images to reduce some of the temporal noise. Now, for imaging outdoors, we do activate the peak tracking functionality, and I'll just try and quickly step through a sequence of consecutive exposures. So what's shown here is the time gate across the pixel array, and then this is depth extracted from a histogram, that's the middle graph, and then we have the histograms corresponding to 2 highlighted macropixels, one in the middle, another one towards the left of the field of view. Now, in the first exposure, no surfaces can be seen, and therefore both of the highlighted macropixels move to the next position. And then similar situation, second exposure, no peaks seen by the pixels, so they keep searching. And then after exposure 4, so we finally see a surface emerging here in the middle. So the second pixel, which is there in the middle of field of view, is now seeing a peak, but it's an outlying bin. So a further time shift will be therefore required. And then this is the first macropixel still peak searching. Now, if you go to exposure 5, so this time most of the scene has been revealed, which is a person sitting next to a tree holding a ball. And now this time macropixel, which is observing the ball, has locked onto the peak. And macropixel 1, which is looking at the background, has detected a surface now, but it still needs a time shift because the being now at line 1. And then by exposure 6, we have most of the pixels having homed in, including both of the highlighted pixels, and indeed most details have appeared in the scene, including the second leg of the swing now. And then if you continue exposure 7 onwards, there's not much of a change anymore, apart from few remaining macropixels also converging. From then on, the frames are pretty consistent. Now, to move to perhaps a more interesting dynamic scene. So this is now longer range. These are somewhat longer range outdoor results, captured at 50 frames per second, and this time it's about dynamic scene. So so pixels not just home in on the surface, but track those surfaces as necessary to keep up with the motion in the scene. And just to show another quick example, so this longer range, still up to 50 meters in open space, and this time this was captured at 100 frames per second. Now, just to quickly show a comparison, basically, of the data obtained in the tracking mode in our versus the conventional sliding mode. So this is data captured in those two different configurations using the same exposure time. And what we have in the sliding mode is the camera basically stepping through 16 times it positioned, and then the first speed detected by each pixel is spotted. Whereas here, obviously, we have the tracking function enabled, so pixels keep tracking surfaces. And what we see is that a factor of 16 higher frame rate in the case of tracking mode, which therefore results in a noticeably smoother depth output.
Isvan, you have 1 minute left or so.
Only one minute left. Oh, sure. Yeah, I'll be very quick.
Or two.
Yeah. This is just a quick example where we enabled the motion detection feature of the sensor, where only pixels with the changing depth are reported and the rest are replaced by zeros. And on the top, so with the original sequence of two people passing a ball to each other, and then on the bottom we see the result only presenting pixel data for pixels with a change in time and position. So this then gives a kind of dynamic vision sensor type output with the movement of the ball clearly visible. And then this we think could help robots using such a time of flight sensor basically respond to activity in their environment with very low latency. And I don't want to run over the time, so I'll skip over the precision and accuracy characterization. It's fully explained in the paper anyway. And there's just very quickly to show you an example, some further work which we've carried out with the sensor. So here we've used it for human activity recognition. So we trained a couple of neural networks based on synthetic data. So one for detecting humans within the field of view, and a second network to determine the activity of the people. And and it's working with a pretty high level of accuracy, and including for multiple people as well. Right, and so that's about it from me. Sorry for running over the time somewhat.
No worries at all. We have some time allotment there.
Yeah. Thank you.
And I see that we have some great questions. Just as a reminder, we're going to pose those questions after the next talk. So thank you.
Thank you.
Thank you. So let's move to the second speaker. Second speaker is Won-Jong Ha. So Won-Jong Ha's affiliation and background is with the Post-Silicon Semiconductor Institute in Korea Institute of Science and Technology in Seoul, South Korea, the Department of Electrical and Electronic Engineering at Yonsei University, also in Seoul, and the Institute of Electrical and Microengineering in the École Polytechnique Fédérale de Lausanne in Neuchâtel, Switzerland. Won-Jong Ha received the Bachelor of Science and Master of Science degrees in Electrical Engineering from Yonsei University in 2020 and 2022, respectively. Since 2022, he has been working toward the PhD degree with the Aqua Laboratory in the École Polytechnique Fédérale de Lausanne in Switzerland, and his research interests include CMOS SPAD structures, silicon SPAD-based circuits, and time-gated Raman spectroscopy. So please, Won-Young, you can start. You can start sharing your presentation.
Yes.
And thank you very much.
Hello, everyone. Nice to meet you all. It's really pleasure to be here. I'd like to thanks to the organizer for the nice introductions and for inviting me to here. I'm excited to discuss my paper, which is about high-performing spot that fabricate in a 55 nanometer BCD technology. Before we begin with, I'd like to discuss about what is single-photon avalanche diode. SPOT is a highly sensitive photodetector that's able to detect single photons. Normally, it consists of the PN junctions that operate in a high reverse bias voltage over the breakdown. So when the photon arrives to the device junction, the electron hole pair is generated and it travels through the junction and collide with the lattice and eventually create more carriers. This process is repeated and eventually create an avalanche breakdown. For this reason, SPOT has a very high gain compared to other conventional photodetectors. And SPOT is usually operated with the quenching resistors. So this is the initial state of the SPOT where the high reverse bias voltage is biased without any current flow. When the photon arrives to the devices, avalanche breakdown occurs. Therefore, high current flows through the circuit. Since the quenching resistor has a very high resistance, the voltage bias to the SPOT go down below down to the breakdown voltage and effectively quench the circuit. And after the recharging process, SPOT go back to the initial state and ready to detect another photons. Throughout this process, but there's a clear voltage pulse observed from the output, and through this voltage pulses, you can know that the single photon has been detected. Due to its high gain characteristics, SPOT is utilized in many biotechnologies where the biosignal is very weak, such as Raman spectroscopy, FLIM, TOF-PET, and NIROD. Moreover, it also utilizes the LiDAR technology, and to briefly summarize the technology, the transmitter emits the photon to the object, and object reflects the photons, and receiver receive this reflected one. And by measuring the time differences of these two devices, we can calculate the time distance between this object and the LiDAR transceiver. Since if the transmitter emit the photon in multiple directions and receiver analyze those reflected photons, we can reconstruct the 3D imaging of the object. Since the reflected photon has a very low reflected photon has a very low intensity, SPOT is a perfect candidate for realize this technology. And we expect that this technology can be utilized in autonomous vehicle to identify the surrounding objects. Therefore, it is important to develop high-performing SPOT, especially if SPOT fabricating a CMOS technology are in great interest to many people due to mass production and the monolithic integration capability with circuitry. However, as the technology scales down, the CMOS SPOT to have high DCR value, which eventually degrades the photon detection probability, which is called as PDP, due to the increased doping concentrations. Therefore, it is crucial to find appropriate SPOT structure with the doping concentrations in low-scale technology. For this reason, I researched and tested different types of the SPOT based on the 55 nanometer BCD technology, and I optimized the SPOT structure and published in the paper as shown in the figure. Both spots share the same front-end design that has a shallow active junction with a p-epi guarding, but the difference is that the one spot has a dielectric edge, which I call it a canyon in the paper, to maximize the photon absorption by reducing the reflection caused by the dielectric layers. Before the fabrications, I run some TCAD simulation to check its characteristics. First, I check the electric field profile. In the simulation, as you can see from the figure on the left, the clear high uniform electric field is formed at the active junction without any premature edge breakdown, which degrades the spot performance significantly. Then I check the breakdown probability profile, as shown in the figure on the right, to know that where the breakdown occurs. As you can see, most of the breakdown occurs at the shallow junction, which I intended to be, and moreover, since the penetration depth of the 400 to 500 nanometer wavelengths is 0.1 to 1 micrometer, we expect the spot has a very high PDP in this region. Lastly, I check the race tracing. I run the race tracing simulation to check the effect of the canyon. As you can see, there's a lot more photons that arrive to the multiplication and have less photons that reflected from the dielectric layer in terms of spot with canyon edge compared to the spot without canyon edge. Through this simulation, I predict that the spot with canyon edge would have a higher PDP than spot without it. And after simulation, I fabricate the devices and run some measurements for the characterizations. First characterization I've done is to check the IB characteristics. And as you can see from the IB plot on the left, I check the characteristic in illuminated and without illuminated conditions. And both spot with and without canyon edge shows a proposed spot operation that's showing very high gain at the breakdown voltage of 16.1 volt. Then I check the light emission test of the spot as shown in the picture on the right to check the electric field to check whether premature breakdown occur or not. As we predicted from the electric field profile, both spots do not show any premature breakdown and shows a uniform E field is formed at the active junction. Then I check the PDP of the spot, which shows the efficiency of the devices. Both spots shows a high PDP at 400 to 500 nanometer region, which we expected through the breakdown probability simulations. And the spot with canyon edge shows a higher peak PDP than the spot without canyon edge. This is also expected from the ray tracing simulation. Then I check the DCR of the spot, which noise characteristic of the devices. Both spot with and without canyon edge shows very similar DCR value because the DCR is dominated by the thermally generated carriers and the tunneling. And both of them are highly affected by the front-end design. And since two devices share the same front-end design, the DCR has to not show any differences. Therefore, DCR isn't affected by the canyon edge. Lastly, I check the timing response of the devices using TCSPC method. And as you can see from the two figures, both timing zeta values is very similar to each other of 68 picosecond and 66 picosecond individually. This is because the zeta is determined by the carrier transit time, such as drift, diffusion, and avalanche multiplication time, which is all connected to the front-end design and nothing related to the back-end design. That's why they have a very similar value. In this slide, I compare the spot with the reported spot fabricated in 90 nanometer or more advanced process in different parameters. And if you see the graph on the left, which shows a peak PDP versus breakdown voltage, My spot shows the highest PDP among them and shows a moderate breakdown voltage. When it comes to the devices that has a lower breakdown voltage, which is very beneficial in terms of the power consumption, 2-spot shows a very low PDP. Therefore, when it comes to find devices optimized for the PDP and the power consumption, I believe that my work is a perfect candidate for it. Then I checked the PDP, peak PDP versus timing jitter, and my work shows the highest PDP and this shows a second lowest jitter value. So in conclusion, in this paper, I reported the optimized spot structure based on 55 nanometer BCD technology, showing the high efficiency, which means high PDP at low breakdown voltage. And currently, I'm developing large spot array with TDC using this spot and for the neutrino detection and LiDAR technology. I hope I can meet you guys with a different paper of this one. This is our lab member with my professor, Eduardo Charbon, and the collaborator. I'd like to thank all of my colleagues and the professor for supporting and helping my work. And thank you for listening.